Alright, welcome to Classical Physics again, and today we're going to be doing a couple things. So one of which is we're going to be calculating weight from mass, which is very simple in the SI units. It's also simple in the English units, but there is something that you need to understand in the English units that you may not have known before. And then after we do that, we were going to be going over the free body diagrams. And so, let's just kick it off with an example. Let's say you have, that's too big of a line, you have a block. And we're going to start out with the SI units because it's so simple. We have a block and it's sitting on the floor, right? And so, this block has a mass. This mass we're going to call 50 kilograms. And if I say I want you to convert 50 kilograms to weight, well, what we know is this is a mass, not a weight, right? And just an aside here, we are on the surface of the earth, just to clarify. So on the surface of the earth we have this block. Its mass is 50 kilograms. We want to know the weight. Very simple in SI units. The weight is a force, and in the SI units a force is measured in newtons, which is a kilogram times meters per second squared. So you can see here kilograms times meters per second squared is the mass times, what do you know that it's a meter per second squared? Well, gravity is meters per second squared, right? So if we take 50 kilograms, so weight is going to equal the mass times the gravity, which is equal to 50 kilograms times 9.8 meters per second squared, right? 50 times 9.8 is 490 newtons. Right? Kilograms times meters per second squared. So whenever we talk about weight in the SI unit, we're going to talk about newtons, at least in physics. So because a newton is a force measurement, and we talk about weight in physics in terms of force. So there you go. That's how you do it in the SI units. Pretty simple, not a big deal. Now let's talk about it in the English units. So this, sorry about that. This is going to be a little muddy at first, but I don't want it to be muddy. So let's get this straight. This mass is going to be equal to, this time we're going to just say 50 pound mass. Remember, anytime we're talking about mass in the English unit, it's pound mass. It's signified by that, right? Now what I don't want you to think here is that we can just say, just like the SI units, and say, well, that just means we have weight equals mass times gravity, and so therefore 50 times, and gravity in the English units is 32.17 feet per second squared. So it's just 50 times 32.17. That would be wrong. Why? Why is that? Okay, so here's why. So in the English units, we're talking about just like in the SI units, when I said a Newton is a force, right? In the English units, a pound force is a force. And weight is a pound force, by the way. We usually don't signify it as force, but we always do in physics, pound force. That way we can clarify between pound force and pound mass. So, there is a difference though. So, 1 pound force is equal to 32.17 pound mass times feet per second squared. This number here should look familiar, since that is also the value for gravity on the surface of the Earth. So what ends up happening, as an example, is if I say I want this 50-pound mass in terms of pound force, if your acceleration is gravity, then this happens. So you have 50-pound mass, and you multiply it by gravity, which is 32.17 feet per second squared. It's mass times gravity, just kind of like you were starting to do up here. That's going to equal 50 times 32.17. That equals 1,608.5 pound mass feet per second squared. That's great, but we want pound force, right? Well, if you remember what we just said, a pound force equals 32.17 feet per second squared. So what that does to us is we now have to divide this, because this is pound mass times feet per second squared. Now we want to know how many pound forces that is. Well, every pound force is 32.17 pound mass per second squared. So we want to know how many 32.17s are in this to know how many pound forces there are, right? So what we do is we have to say 1,608.5 pound times feet per second squared divided by 32.17 pound feet per second squared. Now that equals, I'm sure you already know, divide that by 50. Oops, sorry, not divided by 50. I don't know why I just said that. 50 pound force is what it's going to be. I don't know why I was typing stuff in the calculator. I get too dependent on it. Don't get too dependent on the calculator. You'll be like me. So, what you see here is, I'm going to write this in green. On Earth, the pound mass is the same as the pound force if you are referring to weight only. So, what does that mean when I say if you're referring to weight only? Alright, well this is what I mean. So let's say you have, I don't know, let's say an object sliding on a frictionless surface going this direction. Pushed by some force. Some push force. And this is frictionless, because we'll have to get into friction later. So if this is the only force that I see besides the weight, which is opposed by the normal force. And like I said, there's no friction force. We're ignoring the friction force. So, if that's the case, let's say we're accelerating at 4 feet per second squared, okay? Well, then we would, to solve for force, and we would have to know the mass. So let's say the mass is, well, let's say it's 50 pound mass, just like the last one. So we would have to say the 50 pound mass times, now our acceleration is 4 feet per second squared, right? We're not talking about weight here anymore. And so our force units, let me write that in a different color. Our force units need to be in pound force, right? And if you remember, 1 pound force equals to 32.17 pound mass times feet per second squared. So that's the unit for that. So just like before, we multiply our force times our acceleration. So 50 times 4 is 200. So our force equals 200 pound mass times feet per second squared. But I don't want it in pound mass times feet per second squared. I want it in pound force. So I have to divide it now by 32.17. So now it's going to be 200 pound mass times feet per second squared over 32.17 pound mass feet per second squared, because I want to know how many pound forces are in it, right? So that's divided by 32.17, and our force being applied is 6.22, if you round it, pound force. So that's what's being pushed. 6.22 pound force is being applied on this frictionless surface in order to accelerate this 50 pound mass at 4 feet per second squared. So that's the one thing about the English units that confuses so many people, and it's understandable that it's confusing, because in the metric system you don't have to worry about this step here. Alright, so there's that. And now we're going to talk about free body diagrams. What are they? What are they for? Okay. So, basically a free body diagram, it isolates the body from all other bodies so that a complete and accurate account of all forces on the body can be considered. That's a really, really fancy way of just saying it isolates this body So you're looking at this body and how it's affected by the forces around it and other bodies that are interacting with it. You just isolate that body and you say, what forces are acting just on this, so that I can understand how this body is being affected by the surroundings. For example, if you just have a table and you have a book sitting on the table, and I wanted to draw a free body diagram of just that book. Well, we just kind of isolate this book and we say what forces, outside forces, are acting on that book. So if I just draw the book by itself, I know that the weight, or the mass times the gravity, is acting on that book. I know that a normal force is acting on that book. And that is the only thing that's happening with that, with it just sitting on the table there. I have two forces, equal and opposite, the normal force and the weight. This is a very simple, but still it is a free body diagram. Free body diagram. Let's think of a little bit more complicated one. All right, let's think of, if you go into statics or mechanical engineering, you'll see this all the time. So we have a beam. Let me draw it a little lower than that. We have a beam, and the beam is resting on two supports. So it's resting on two supports, and we have a force. Actually, let me just make those two rigid supports for you. And you have a force here. So let's draw a free body diagram of this beam. So what we'd do was we'd just redraw the beam. We say, yeah, we have this force here, but we also have two reaction forces. We call it reaction A and reaction B. This is the free body diagram of that beam. Let's say you had a more complicated example. Let's say you had a piece of C-channel or something. Whoa. So you got this piece of steel, C-channel, and it's got this little connection to the ground, and this connection goes over, comes up, comes over again. So this is all the ground, right? Now you also have, let's just draw a free body diagram of this one by itself. Okay, so we're going to draw the free body diagram of this. We'll just draw this, oops, sorry. We'll just draw this simple square here. And we'll just put, this will be our mount. Okay, so on our mount, we're going to have a reaction this direction And then if you notice, the weight is about here and about the center here or so. Mass times gravity. And we're also going to have a reaction right here, right? And this reaction, though, is going to be normal to the angle. So there's the normal reaction there. I'm just going to call this, let's call this point B, point A. I'm going to call this reaction A. I'm going to call this reaction B, Y. And the reason why I say Y is, if you notice, just think about it physically, this beam is going to want to slide down, right? I mean, I know it's pinned, but it's going to want to slide down. It's going to be prevented from doing so by that hinge. And so that means that you've got this weight, that you've got a reaction in two different directions. So not only are you supporting it vertically, you're supporting this lateral movement that it wants to do, but is prevented from doing because of this reaction B. And if you think about it, you have some kind of reaction resultant B in that direction, right? All right, let's undo that. Okay, so that would be the free body of that, and then that would assume that's X and that's Y. So why is this important, and what can we use it for? Well, we will use these free body diagrams and these force vectors and their directions in order to solve for unknown reactions or unknown forces. That can be the first step in us then finding out maximum stresses in a beam or something like that. So when we look at these force diagrams or free body diagrams and determine their forces, we begin to enter into the world of statics. So what is statics? Well, statics has to do with equilibrium. And you kind of know what equilibrium is just by the word, right? If just like in our book example, when the book was just on the table and there was no forces acting on it, it was an equilibrium. So all of the net forces, so I'll say net forces in this case, was equal to the weight plus the normal force. And if you took this direction to be positive y, then that would be negative weight plus the normal force, and they would equal 0. And then we would say that is in equilibrium. The net force acting on the object is 0. If the net force was not 0, then we would say that that net force is the primary influencing force on the object, and that would make sense, right? If you had an object and you had a small force here and a very large force here, the net force would be in this direction at some magnitude of the summation between those two forces, force A and force B. And we would say that that resultant force, or the net force, is the influencing force, because that's the force that's going to have the impact on the object at the end. So, how does this help us further, as I was alluding to? So, we've just stated that when something is in equilibrium, there is no net force. All the forces acting on it will end up either canceling out, right? Canceling out in some way. So that would mean that it's in, we would also call it static equilibrium, right? So it's in static equilibrium. I don't know how else to say it. It's because it's the way to say it. So let's do a really good example here. And I'm going to do, say we have this situation here. This is this corner here. And we have this ball. This ball is hanging with a junction by these wires. We'll call this tension 1, tension 2, tension 3, and we'll say that the angle on this tension here is 30 degrees. Right? And so you have, let's give the weight of this guy. So the weight is of the ball equals to 125 pounds, I think is what I wrote down before. Make sure. Yeah. So 125 pound, and I want to say force here because we were talking about the force of weight here. So the weight of the ball is 125 pounds. And we want to know what is the tension in T2, which is this guy right here. We want to know what tension is being experienced on that cable there. Okay, so here is the way you always approach these problems. If it's, we already know that this is hanging here and it's still. It's not falling, it's not swinging, it's not lifting, it's hanging there still. So because of that, then we know this ball is in static equilibrium. This is key. If it's not in static equilibrium, none of the rest of this will work. It has to be in static equilibrium. And this is because, like we just said, it is just hanging there. It's not falling. It's not no movement. It's just hanging on these cables, and it's in static equilibrium. So because of that, then the sum of all the forces should equal 0. That is the main key to absorb in this. And because of that, we can separate these and say, well, then that means the sum of the forces in X equals 0. And that means the sum of the forces in Y equals 0. So let's go ahead and say, well, what's the sum? Sum of forces X equals 0, sum of forces Y equals 0. So we're looking at all of the sum of the forces in X. And so if you look at all of these in based on the diagram, we know that I'm just going to write over here on the side here. We know that T3 in the X direction, the force is going to be 0, right? Because it is a vertical member with no forces other outside forces acting on it, and it's in static equilibrium. So the tension in X for 3 is 0. The tension in Y for T1, so T1 here in the Y direction is 0. Because if this is in static equilibrium and this is the way that it looks, then that means that there is no Y tension on T1. Okay. So X is going to have T1, and it's going to have if you look at this, if you separate this like in a triangle here, you can see that the x component, if you remember from vectors, it's going to be t2 times the cosine of 30, right? And the force in y is going to be, because this is positive, negative t3, and then plus t2 sine of 30. Okay. And let's look here. So we only care about what T2 is. And so we do know T3, or basically the force in T3. And that is, it's right over here. So T3 in y is going to equal the mass times gravity, or the weight, which equals 125 pound force. So that's the force down. So the sum of force in y is going to equal to negative 125 pound force. And the opposing force would be T2 in the y direction, T2 sine of 30. And so you rearrange this equation, you get 125 pound force over sine of 30 equals to T2. And if you do 125 over the sine of 30, you get 250 pound force equals T2. So that is why free body diagrams matter, because force directions matter. Like this ball can easily be shown, instead of this whole thing, just to picture it a little bit better, I should have done this at the very beginning. This is what you get when you've done so many of these, you skip steps. The free body diagram of this would look like this, this, and this. So if you do that, that'll help you with your signs. So you know that this is going to be, if your convention here is x, y, and then this is positive and this is positive. So we know that that weight is negative. We know that this will be a positive tension. This would be a positive, and then this would be a negative on this side. So T1, if I look back on X, it actually should have been negative. So yeah, so there you go. And that makes sense, right? Because these should end up equaling 0. So I should have done this at the very beginning so that it was all clear, but that's the free body diagram of this situation here. We've got a force going down, supporting tension coming back up, supporting tension going toward the wall. So that will help you with your signs. And yeah, so that's an example of a static equilibrium problem. And you can notice here that we didn't even have to solve here for the sum of forces in X, because we got everything we needed to know from the sum of the forces in Y. If we wanted to, we could go on and solve for T1, since now we know T2. But you can do that on your own if you really want to. I'm running out of space. But if you want, that's a good exercise. That's for you, I guess, if you want to just do the plug and chug thing here. But you can just put T1 on the other side of the equation, because keep in mind, this sum of forces in X is supposed to equal 0, right? So what I could do is, instead of writing sum of forces in X here, you can picture this as just saying 0, because we know the sum of forces in X have to be 0, right? That's what I did down here. Switch this to the other side. Just treated this as 0 because the sum of forces in Y have to be 0 in order for it to be in static equilibrium. Alright, so yeah, so that's an example of static equilibrium and free body diagrams, how they help in static problems, so that you can visualize what direction forces are in, how they are affected, or affecting the mass, or whatever you're dealing with. And yeah, I guess that's really all you can say about it. But just repeat this lecture if you kind of feel a little bit lost. You can message me, I suppose, and I can try to help you out with any specific questions that you have. But if that's it, till next time.